A complete graph is a graph that has an edge between each pair of vertices. An edge, we've seen this twice before now. An means how many? One. So I just got a message. So the graph on the left is a complete graph because there is an edge between every pair of vertices. So A goes to B to C to D. B goes to A, C to D. C goes to A, B to D. D goes to A, B, C. That'd make a great song. So that's a complete graph. The graph on the right is also complete. A goes to B, C, and D. Blah, blah, blah. Finish the song if you want to. Now, of those two graphs, which one is the nicer one to look at? I would say the one on the left. It looks much more organized. They're technically equal graphs. However, when you're drawing your complete graphs, it's best to keep it as a polygon. So triangles, squares, pentagons, hexagons, septicons, decepticons. I don't know what the names are after a while. Octagon, I got octagon, that's cool. So when you're drawing your complete graph, make it a polygon. That's the best ones. All right, good. Now, every complete graph with three or more, I did it again, with three or more vertices, has at least one Hamilton circuit. So we have 4 vertices. That's great. If you had a 3-vertex complete graph, that would just be a triangle. A, B, C. So notice a complete Hamilton circuit here would have been A, B, C, A. Over here we could have had A, B, D, C, A, for example. There's a whole bunch of these. But that's the rule. You need at least 3 or more to have at least one Hamilton circuit. Because if you only had 2 vertices, for instance, A, B, then that right there is a horribly drawn complete graph. But there's no Hamilton circuit because once you go to A from B, you can't get back. So, what are you going to do? Now, there's a way to know how many Hamilton circuits you can have. And I throw in a word here. Let me actually change colors real quick. So if there are n vertices in a complete graph, then there are n minus 1 factorial Hamilton circuits. We saw the factorial earlier. So we have 4 vertices, so our n is 4. So 4 minus 1 factorial, well, that's the same thing as 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. So there are 6 Hamilton circuits. Now this is assuming that we know where we're starting, meaning we know we're starting at A, or we're starting at B, or C, or D. The starting place will have to be declared. And again, for the traveling salesman problem, that's like the warehouse, going back to your house. So for example, we could have, wherever my cursor is, we could have A, B, D, C, A. We could have A, C, D, B. Oh, that's supposed to be a B. B, A. We could have A, B, C, D, A. We could have A, D, C, B, A. And we can have A, C, B, D, A. Or A, D, B, C, A. That's assuming that we're starting ending at A. Again, it'd have to be declared. So if you traced out all of these, you'll realize that they're all Hamilton circuits. We pass through each vertex once, and we start and end at the same vertex. However, as it says there, half of which are essential. Now that's my word. That word's not really in in a book or anything, in any other book, I should say. What I mean by that is, notice that, and I did this on purpose, the column on the left is the reverse of the column on the right. So if you're traveling along, so imagine that A was your house, B, C, and D are errands you have to run, like post office, Best Buy, whatever else. So if you went from home to Best Buy to post office to Target to home, that'd be the same distance traveled as if you went from home, Target, post office, Best Buy, back to home. I think I did that backwards. I don't know. It's way too early. So since it does not matter in terms of the total time taken or total distance traveled, the order in which you go, I'm calling the first column, or I could have called the second column, the essential ones, because it's unique to the other ones in that column. So half of which are essential. So there's 3 that I'm going to consider to be essential. It does not matter which column you pick, by the way. So that's the whole idea. Now, the only time it would make a difference, honestly, is if it's like late at night and the post office closes at 5 and Best Buy closes at 9 and Target closes at 11. Well, you'd want to go in the order to which you get to the stores that are open on time. But assuming it's morning and you got nothing else to do, then we don't have to worry about going in a very specific order based on time of day. So again, if the starting point has been declared, then there are n-1 factorial Hamilton circuits. Half of that are considered to be essential. Okay. And before we go any further, a graph with values along the edges is called a weighted graph. Now, these weights could represent anything. It could be distance in miles, kilometers. It could be a number of customers along a route. Yeah, anything you could think of. So do not assume that the graph is proportional to the weight. For instance, AB has the same length as DE and AD and BE, but they all have different weights. So do not assume that the AD has to be shorter than AB. Not true whatsoever. When you are labeling your weights, please write neatly. You don't want to make it look like the weight is on a different edge than what you intend. So that's a weighted graph. We'll need that in this section and the next one. Okay, so this is the traveling salesman problem. The goal is to find the shortest route, or route, however you want to pronounce it. That is the optimal Hamilton circuit that passes through each set of vertices exactly one time. Now, optimal here means best, not biggest. There's 2 ways we're going to solve the traveling salesman problem. That is what's called the brute force method and the nearest neighbor method. As you'll hear me say, the brute force method is going to be one that gives you the direct answer, but it takes a while. The nearest neighbor method gives you an approximate answer, but it goes faster. So they each have pluses and minuses. And, oh, that's right. And note, the traveling salesman problem focuses on finding the shortest Hamilton circuit. As we're going to see, that means the one with the smallest weight. However, depending on the scenario, you might want the one with a larger Hamilton circuit. For instance, let's suppose that those weights represented houses giving out candy on Halloween. Well, if you're a kid looking for some candy, then you'd probably want to take the larger weights because that means you get more candy. As long as they're Reese cups, that's really all that matters in life. All right. So there are 4 steps to the brute force method. 1, draw the corresponding complete weighted graph. That might already be provided for you. 2, make a list of all essential Hamilton circuits. 3, determine the sum of the weights on each of the Hamilton circuit. And assuming that you want the smaller weight, the Hamilton circuit apparently, with the smallest weight is the optimal solution. That is the brute force method. So again, you're going to see with 4 vertices, there's a considerable amount of work. 5 vertices. Well, 5 minus 1 is 4. 4 factorial is 24, half of which is 12. So if you had 5 vertices, you'd have to do 12 essential Hamilton circuits. Gah. So that's why you're not going to be getting a lot of vertices, because these take a while to do by hand. So if you would, please watch Brute Force Method.